programme is about black holes. We're going to introduce them in a rather unusual way and bring in a little magic. With me, Professor John Brown, the astronomer royal for Scotland, who, as well as being an astronomer, is also a highly accomplished magician. Also from the University of Glasgow, Fiona Spirits, and to complete our magic circle, Chris Flintoff. Well, let's begin. John, back to fundamentals. What exactly is the connection between astronomy and magic?
Well, for me, I kind of think of the cosmos out there as a cosmic magic show, and astronomers are here to try and figure out how the universe does its tricks. I got interested in magic about the same age I got interested in astronomy. The new program started. And way back then, all I had was a little plastic telescope. Couldn't see very much, pretty dull, really limited, but things have changed enormously in the last 50 years. We've gone through radio astronomy and all that, and all these amazing things we didn't know about before. And as we've increased the number of wavelengths we can observe progressively, we see more and more in the sky. So magic gives us a new way of looking at things, and it sharpens the wits for understanding curious phenomena.
Well, black holes and black magic. Let's start then with black holes. What are they, John?
Well, in brief, a black hole is an object which has the strongest possible gravity. If I try and throw something off the Earth, I have to throw it very fast, about 10 kilometres a second or so. But the heavier and more dense an object is, generally speaking, the faster you have to move to escape from it. In the case of a black hole, the gravity is so powerful that even travelling at the limiting speed of light, nothing can truly escape from it.
Well, Fiona, if we can't see these things, how do we know they're there?
That's a good question. The best observations that we have come from around about 6 years of observations of stars orbiting the centre of our own galaxy, the Milky Way. When you reconstruct the orbit of these stars and then work out the mass around which they must be orbiting, then it must be a supermassive black hole or of millions of times the mass of our own sun.
It's amazing to see this picture of stars actually moving, not a simulation, not a guess.
These are real observations of real stars in our own galaxy orbiting a supermassive black hole.
And we think that something like this lurks inside almost all the galaxies now, and they can have some very strange effects, can't they, John?
Yeah, they can indeed, actually. Okay, let's just say a little bit about the nature of gravity. Newton had this idea of gravity as action at a distance, and very effective for calculating orbits and so on. But Einstein described gravity in a more prosaic way, that gravity is actually a fundamental property of what we call space-time. If you think of space, empty space is being flat, like this sheet here, and things in the empty space move pretty much in straight lines, like this. Nothing to perturb them. And what Einstein did was to describe gravity as the presence of matter. Use the magic wand to symbolise, say, a thing like the sun or the earth. What that does is to bend space-time. So gravity is bent space-time, and in bent space-time you don't move in a straight line anymore, you move in an orbit. So
that's what gravity really is.
Gravity, essentially, in the terms of modern general relativity and so on, is visualised as curvature of space-time. And, the stronger the curvature, the faster the orbit. If it were not for the sun bending space-time, we would fly off the straight line and freeze to death. It's bent space that keeps us near the sun.
So what happens when you get a larger star or a bigger mass as things increase?
Well, basically what happens, as the bend becomes greater and greater, the orbits become faster, the same distance and so on. So if the sun was heavier, we'd be whizzing around it faster in order not to fall in. As you go to more and more massive things, you eventually reach the limiting case of a black hole. And to really understand one of the most fundamentally amazing properties of a black hole, we could demonstrate. I use a rather small piece of space-time here, and a shot glass here. And I need to borrow somebody's finger. Perhaps I feel like that. What I'm going to do is, just so there's no sneaky business, I'm going to make sure that this is well isolated about space-time. Fiona's going to represent a small mass to be able to just see space bends, and then increasing the mass will eventually reach a limit of the black hole. Things disappear, but without actually leaving a hole in space-time. So a black hole is the limiting case where space-time becomes so bent that a part of it is almost like a water droplet. It snaps off, and this becomes a detached part of the universe.
What happens if you're really close to a black hole?
It's a matter of thinking, starting to classical ideas of very weak gravity. If you're on a thing like an asteroid or the moon, gravity's pretty weak, so if you drop something like this, it falls rather slowly. You go with a cup of tea. Whereas on the Earth itself, it falls rather fast, and things fall more and more quickly as you get closer and closer to a black hole. And there's all these magicians, some of them quite famous, who do spoon bending. But if you have a black hole, the beauty of a black hole, the gravity is so strong it spontaneously makes things bend like this. Just the sheer gravitational force of this black hole is quite sufficient to bend a good solid plastic bar, for example.
What happens if you fall into a black hole?
Well, there's three possibilities. Everything's equal. Are you likely to stay the same length in your black hole? Very unlikely, so I think we can probably discard that possibility. There are actually two things that can happen to you as you approach the black hole. One is, if you were to stand on a platform which supported you, the black hole's pulling you down, what happens is you become terribly short and squished up. Now, that's what would happen to you if you tried to stand on a platform or a table or something near a black hole, because you would get squished down, actually turned into just a thin pool of liquid. But if you fall in freely, what happens to you? You undergo what's called spaghettification, and you actually become very much longer. And the reason is that the gravitational pull in your feet is much bigger than the pull in your head, and as you fall in, you'll and become longer and longer. Spaghettification is the correct technical term.
But we might want to find out about what life is like near a black hole. So what would happen if we tried to send an intrepid graduate student, say, down into the centre?
Beyond.
Yeah, could we get a signal back?
Well, matter can't escape a black hole, and in fact, as John said, even travelling at the speed of light, you can't escape a black hole, so light itself doesn't escape. So our traditional method of sending a signal, if we were to send a signal to Patrick on Earth, he wouldn't be able to receive it if we were beyond the event horizon of the black hole.
That's the edge, if you like.
That's sort of the boundary of the black hole. If we were to realise that we were about to fall into it and maybe wanted to send a help signal back to Earth, what happens is that the gravity around the black hole curves space-time so much that this affects light. It redshifts it as the light tries to climb out of the gravitational potential. So if I were to nominate John to throw himself into a black hole.
If I leave my signal too late, if I'm actually getting into the black hole beyond the event, I've had it, I can never get a message home. But just as I pass this point, if I sent a blue signal, as Fiona says, like this to Fiona,
and then by the time it gets to Patrick, it'll be redshifted.
And if you really start too deep, what happens is it gets redshifted to zero and there is no information whatsoever, no energy left to receive.
So you'd have no way to know that John had fallen in.
As you get closer and closer to the event horizon, it therefore becomes harder and harder to get any information out at all.
Exactly.
But some radiation can escape from a black hole. This is what we call Hawking radiation, after Stephen Hawking, of course.
That's right, in a sort of classical gravitational sense, nothing can escape, but you have to involve quantum mechanics, and particles is rather interesting properties in this quantum world. We used to think the vacuum like this was sort of completely boring and empty, no interest to us whatsoever. But actually, we now know that the vacuum isn't truly empty. It's seething with invisible energy, virtual particles that pop in and out of existence like this, appear for a moment, you get a particle and its antiparticle, and then they vanish again back into their virtual invisible state so quickly we can't see it. However, if you're in a gravitational field, let's say a slightly weak gravitational field, these particles may hang around for a bit like this, and you can get into a situation where if you have a very strong gravitational field, for example,
if you're near a black hole
in particular, if you get close to a black hole, so one of them can be permanently separated from it, then this one may be left to annihilate with an ordinary particle in our outside the black hole, and that turns into radiation, and we could see it as Hawking radiation. And what you then end up with is a situation where you could have continuous radiation like this, as these particles are turned into real particles and annihilate, half of them go into the black hole, half of them annihilating and producing what's called Hawking radiation. So that black holes do in fact radiate, they're not truly black.
Fiona, what's the effect on the black hole when this is happening?
The black hole loses a small amount of energy to create this particle-antiparticle. If the antiparticle or the particle were to drop back across the event horizon, the black hole gains a small amount of energy back, but it has lost some energy as one of the particles is radiated away. So this effectively, if it happens a lot, then the black hole will start to evaporate and shrink. and
What happens then?
Perhaps eventually it disappears.
Especially small black holes, they radiate quite powerfully. The bigger they are, the lifetime is much greater.
This could be the future of the universe, because more stars are dying than are being born. We're going to end up with a lot of black holes, and maybe the future of the universe is just gently radiating black holes. It's rather a depressing
Rather depressing, not for a long time yet, luckily.
No, we've got a while yet.
We have indeed. Of course, the boundary of a black hole, the event horizon, you can't actually see it.
I think that's true. You can see its effects. If you had an object, a clock, or a volunteer moving more and more close to a black hole, then certain things, we saw the spaghettification and so on, you can observe changes in their signals, for example, as they approach the event horizon. Once they're beyond this event horizon, they're completely invisible.
We can also potentially measure the effect on space-time round a black hole. There's Gravity Probe B, a satellite in orbit around the Earth just now, is trying to do just that. What happens is, as the black hole is rotating in space, it drags space-time round with it in an effect called frame dragging.
We've heard a lot about gravitational lensing, John.
Yes, again, the powerful gravity of the black hole bends light itself, changes the frequency, the colour of light, but it also bends the path of light, and we see that, and there's a wonderful picture of a thing called the Einstein cross, taken by the Hubble, and the way one can symbolise that, if you imagine this negative image of the sky with a quasar or something here, if you have a heavy object, especially a black hole somewhere near the path, what happens is the light bends. It's not a perfect lens. It can do rather interesting things to the light, and you can get multiple images. So move the black hole a little bit and get like this. Now, depending exactly where you are relative to the black hole, you can get maybe 33 images, or maybe 4 images, or maybe 1 image, or maybe 6 images, and so on, and 3 and such. And it's quite fascinating that how the sky can behave this way. Of course, this is just a piece of magician's trickery. It's a classic piece of what they call misdirection, because you tend to believe that you'll hear something like, I don't know, I'm just conning you as a magician. It's all bogus, because you never really do see 3 images. You actually only ever see 2. It's all done with clever obscuration. Only if you truly had a black hole would you ever be able to. Of course, what I'm doing with the case of 6 and 4, I tell you it's 6, I tell you it's 4. Only if there was really a black hole here could you actually get this gravitational lensing effect and really see 6 objects like that. And the same way, only in the presence of a real black hole would you be able to see as many as 3 on that side. And of course, the ultimate limit is when we take our white rabbit out of here and get really very close to the black hole, you can actually get as many as 8 images. So how many images you see depends on the geometry where you are relative to the black hole. And there's also information about the black hole mass, which is interesting.
We can use these lensed images to reconstruct what's doing the lensing. So sometimes it's a massive galaxy, sometimes it's a galaxy cluster, but when you reconstruct the mass and the distribution of the mass, then you can infer that there's potentially a black hole there that's doing the lensing. So that's more evidence for black holes existing.
It all sounds highly complicated. Fiona, how do these black holes form anyway?
Well, we think it's a final stage in the evolution of a very massive star. We know that massive stars, more massive than our own sun, when they die and they run out of fuel in the centre of them, the fusion switches off, and what happens is the star collapses in and then rebounds out whilst the core has collapsed to form a neutron star, more commonly, and the outer shell is thrown off, and we see this as a supernova. However, if the star is much more massive and much higher energies are involved, then the core can collapse into a black hole and the outer layers are thrown off, and we see this as a gamma ray burst, which is much higher energy.
It's always confused me because you've got 2 processes. The thing starts collapsing, but most of the material ends up shooting outwards and actually flies off at huge velocities. How does that happen?
It seems very counterintuitive. If you drop something through gravity alone, it can't bounce up any higher than the energy you've given it by dropping it. However, if you were to have a very large concentration of mass in the centre when you were to drop it, you would find that it rebounds an awful lot with a lot greater energy than you gave it to begin with.
So the red ball is the outer layers.
That's the outer layers, and you've got your concentration of mass at the centre.
Now, these things happen very quickly. We see a flash of high-energy radiation, but how else can we get information about such a rapid event?
We also know that the energy is given off in the form of gravitational waves. This isn't electromagnetic radiation. This is perturbations in the fabric of space-time itself. Ripples along, for example, the rubber sheet in the universe. And we can hopefully measure these through different detectors. We have several ground-based detectors, and we're also planning on flying a satellite-based detector called LISA in around about a decade, which is hoping to measure these gravitational wave signatures.
And LISA's made up of 3 separate spacecraft. How do they work?
Well, they're all connected by lasers, and it's based on a Michelson interferometer. You could measure the difference in the path length of these lasers due to the stretching and the compression of space-time from gravitational waves, and the interference pattern from these coherent lasers will be affected due to the change in the path length.
But this effect's very small.
Yes, the magnitude of these perturbations are so tiny. They're smaller than the width of an atom, which is obviously a great challenge to measure them, but we hope that the detectors are getting almost sensitive enough that we'll be able to detect these signatures.
And you could get some very strange signatures indeed.
Yes, there's potential perhaps that our view of the universe is perhaps not as complicated as it really is. We think maybe the universe exists on a brane or a membrane, like your rubber sheet in space-time, and we're confined to this membrane, and all our radiation and our light and our matter is confined to this membrane. However, there could be multiple universes, each existing on their own brane, and these are connected and they exist in what's called the bulk. And the separation of these membranes is another dimension in itself. So if gravity were to exist in the bulk and perhaps leak onto our own membrane, our own universe, which potentially explains why gravity is such a weak force compared to the other fundamental forces in the universe.
It sounds strange saying that gravity is a weak force, but this is a problem.
Exactly. I mean, it's strong enough to keep us on the Earth, but relative to the strong force and the nuclear force, it's many orders of magnitude weaker, and we don't really know why this is.
Someone else pointed out that a small fringe magnet is enough magnetically to defeat the gravity of the entire Earth. It's a good way to see how weak gravity is, but nonetheless we're alive because we're kept out by gravity.
So I can just about hang on to the idea of these different branes and an extra dimension between them, and black holes might be the connection.
Possibly, if something were to fall through a black hole, the black hole might penetrate through the bulk and connect all these branes together. Therefore, we might be able to get a gravitational wave signature from this bulk, which will enable us to measure this extra dimension that separates these universes.
So it's amazing to think when LISA flies in the next decade or so, we might actually detect other dimensions.
Exactly. That's possibly the only way we may have to prove these extra dimensions exist.
Any chance for contacting them?
No, not as far as I'm aware. We don't really know what happens when we send our signal into the black hole. It wouldn't necessarily come out in their universe on the other side.
Well, this brings us on to the idea of parallel universes. John, do you really believe in parallel universes?
Well, not passionately, but as a day-to-day solar physicist, nuts and bolts scientist, I'm a bit sceptical, but nonetheless, really exotic and interesting idea. And a question I'm very often asked is what caused the Big Bang? And view of what we've just been hearing from Chris and Fiona, there may be a connection between the Big Bang and brains and so on, and it may well be that universes like ours actually the Big Bang from which we emerged really came from a black hole elsewhere in the multiverse. And we have demonstrated this. You have this stuff emerging out of the other side of the singularity of a black hole, and suddenly once it begins to warm up a bit and realise it turns into another universe like ours.
Absolutely fascinating. So thanks to our members of our Magic Circle. John, Fiona, thank you very much. And now on to our news notes. We'll be talking about neutron stars, and Chris, we now found the nearest neutron star.
Yes, and it's rather an unusual one as well. It's in the constellation of Ursa Minor, about maybe as close as 250 light years away. But it's rather odd. First of all, it's on its own. Most neutron stars are discovered in binaries. This is only the 8th one to be discovered as a solo star. And secondly, it shines in X-rays. That's how it was discovered, looking through old ROSAT data, actually, and then following up with the SWIFT satellite. So it shines in X-rays, but it's very, very, very faint in all the other regions of the spectrum. In particular, the astronomers used the Gemini telescope, one of the largest telescopes on Earth, to look for this thing, and didn't see anything.
No luck.
No, so what we need to do now is study it and try and understand why it's bright in X-rays but not emitting in anything else. So keep an eye on this one.
Can it be the first or an entirely new kind of object, do you think?
Well, people have predicted that there are what are called quark stars, which are denser versions of neutron stars, but they're very theoretical. Something odd is going on. Let's wait and see what the rest of the data tells us.
Now, turn now to the most famous variable star in the sky, Mare Cetus, much further away, has a period of 332 days, and it can get quite bright, first magnitude, but at the moment it's well below naked eye visibility. It passed its maximum last winter.
Yes, and this is a star that's been studied for more than 400 years. This is the first variable star to be discovered, and it's still surprising us. Astronomers were looking at data from an ultraviolet telescope, which was supposed to be looking at galaxies, and they discovered what looked like a comet.
A tail!
Exactly, it's Mira, with its tail stretching 13,000 light years out behind the star. And what's happening is Mira is an old sun-sized star. So it's gone from being a normal star like the Sun to a very large red giant. And it's giving off material. It's also moving quickly through space. So as it rushes through space, it gives off this material, and we get this beautiful tail left behind, shining in the ultraviolet. Now that tail's important. It contains carbon, oxygen, nitrogen. It's rich in what we call heavy elements. And so this is a way by which giant stars seed the universe around them. They're giving out material.
And the total mass of the material in that tail, about 3,000 Earth masses.
Yes, it's significant anyway. Mira will eventually form a planetary nebula and then a white dwarf at the centre of that, but for now it's producing a spectacular show.
And we'll now go and look for tails with other Mira-type stars. We still have plenty.
Yes, no one had thought to look before, but I'm sure there'll be plenty more discoveries like this.
Now let's come much further into it, to our own solar system. In then to the planet Uranus, discovered by Herschel in 1781 for the period of 84 years. It's a strange planet, and in 1977 it was found to have a system of rings, not bright, icy rings like Saturn, but dark and obscure. And now, for the first time since then, we got the chance to see them age-wise on.
Yes, as you say, they were discovered in 1977. The Voyager 2 probe had a good look in the mid-80s, and then really we haven't had a chance to see the rings of Uranus since then. Now, with the rings edge on, we can see them silhouetted against the planet, not in the small telescope, the professionals can, and it's a really good chance to understand them. Now, it's far too early to say what the results are. There are changes since the Voyager mission, but there's one more chance. We've just had, on August the 16th, the second of the 3 opportunities. Next February is the last chance for a while to see the rings of Uranus edge on. So,
for a long, long time.
So let's see what results they get from that. It would be fascinating to understand why these features are so different from Saturn's more famous rings.
Uranus is a strange planet altogether. Now, to much further into come to Mars. The launch of a new Mars probe, Phoenix.
Main engine chamber pressures looking good.
This will land on Mars at the end of next May, and really carry out a search for life.
Yes, it's good that everything's going well with Phoenix. This is a probe that's aiming for the northern polar region, not right at the pole where the ice cap is permanent, but in the region of Mars where the ice covers the surface in winter.
That's as Borealis.
That's right. Phoenix is aiming to land in summer, so it'll touch down not from airbags like Spirit and Opportunity did, but with rocket motors that hopefully lower it gently to the surface. And then its mission is to dig below the surface and see if we can pick up the ice that we know is there. We've seen from orbit, and particularly from radar measurements, that there is a lot of ice underneath the surface. But what's its chemical composition? Could it support life? What's the nature of the subsoil material? And Phoenix has the opportunity, it can't travel across the surface, but it can dig down. And it's going to be a fascinating mission.
The landing is going to be very risky indeed.
Yes, they know what they're doing. I'm confident that Phoenix will be okay, but it's not the tried and tested airbag mission. This will be the first mission since the Vikings to use rockets to do. It reminds me a little of the Apollo lunar landers, this controlled descent onto the surface. They don't have any choice. The probe is too big, and if you want to land in that region, the atmosphere too thin as you come in to use airbags. You've got to land with rockets.
Will this show any trace of life on Mars?
I'm not sure it will, but it will tell us a lot more about the possibilities. The other thing to note is that Phoenix only has a limited lifetime because by the end of next Earth year, the ice will be advancing from the North Pole, and if Phoenix is still operating, we might just get this amazing image of the glacier building up around the spacecraft, which will be frozen over the winter.
Let's hope we do. Phoenix is on its way because Spirit and Opportunity are still functioning. They've been threatened by a major dust storm on Mars, but I think things are looking a bit brighter.
They are. I'm rather reluctant to say this in case we tempt whatever gods operate on Mars, but things are brighter. This is a massive dust storm, the kind that happens on Mars every 5 or 6 years or so, and it's beginning to alleviate. Spirit has started moving its robot arm again. They've got enough power to do that, and Opportunity is waking up slowly. The big danger now is that the dust dropping out of the atmosphere, which will take months to clean completely, might drop onto the solar panels of the rovers, further reducing their power. But hopefully the worst is past, and if you remember, Opportunity is about to head into Victoria Crater, a most exciting time, so let's hope the worst is now over.
I feel they're going to survive, you know.
I hope so.
During the maximum of the Perseid meteor shower, of course, we had our big meteor party here, and we got some Perseids too.
We did, and lots of people from all over Europe did. I get the sense the shower was slightly disappointing.
It was.
It certainly wasn't as extreme as the big Perseid storms of the early 90s, but we saw ourselves 40 meteors an hour, which isn't too bad.
And of course we had a good sky and no moon, so it should have been very favourable. I was a bit disappointed it wasn't Richona.
Yes, well maybe next year. You never quite know what, even a shower as reliable as the Perseids, you never quite know what they're going to do.
Perseids are like cats, unreliable. And one more important news note, the shuttle Endeavour has been brought back to Earth a day early to avoid very nasty tropical storms. They're down safely and we're all very relieved.
Yes, another successful mission to help construct the International Space Station. There had been some concern because they'd spotted damage to the bottom of the shuttle, similar to that which caused the Columbia disaster. Columbia, of course, broke up on re-entry to the Earth's atmosphere a couple of years ago. Now, this is the first time, I think, where they've spotted such damage, decided it was too minor to bother fixing, and left it alone. And luckily, all was well. So the shuttle successfully on the ground.
And of course, the shuttle program is fairly being completed now, but there's one very important mission left, a vital one, to go and repair the Hubble Space Telescope.
Yes, Hubble is really on its last legs at the minute. Almost all the instruments have failed. It's only just being able to navigate and control itself with its remaining gyroscope, so we need another shuttle mission. And let's just hope nothing goes wrong between now and that mission to further delay the program. We need Hubble, and this is the mission that we need to fix it.
And now, into our own moon. We have the SMART probe, which was most successful and took amazing photographs. Some gave those photographs of the Mare Humorum, a basin formed by a single impact.
Yes, and SMART is no more, as you know, but they were still analysing the images. And what you can see here is the results of that impact. In these incredibly detailed images, you can pick up the faults and the associated surface features that were caused by that impact. In fact, you can see the effect of what's called a mass con,
underneath.
a concentration of mass underneath the surface, which might well be the remnants of the thing that caused the impact.
And of course, Oceanus Procellarum, a larger of the lunar seas, not formed in the same way, may have kind of outflow, associated with the formation of the Mare Imbrium Basin, just over 3.8 thousand million years ago. No mass on there.
No, and as you can see from the SMART images, it's a very different place from the impact basin we were just talking about. And it's confirmed that theory that you were talking about. This is a feature associated with the nearby Mare Imbrium. And the other nice thing is, some of the youngest rock ever found on the moon has been detected here. We're talking about basalt, which is only 2 billion years old. Now, by Earth standards, that's extremely old, but for the Moon, that's relatively young, and it'll be interesting to work out the details of how that formed. Some sort of late volcanic activity, I would guess.
It's good indeed. Well, we don't know all about the Moon by a long way.
No, there's a whole host of spacecraft on their way to the Moon from India, China and Japan, as well as the Americans are all launching lunar probes in the next year or so. It's a good time to be thinking about the Moon, your territory.
It most certainly is. Chris, thank you very much.
Pleasure.
When we come back next month, we're going to go to Jodrell Bank and see the world's most famous radio telescope. Until then, good night.